Welcome. Today's lesson is entitled The Complex Plane. And so what we're going to be doing over the next couple days is looking at representing complex numbers in an entirely different form, and then actually performing operations on those complex numbers using this different form. And so we'll go ahead and start that out at the top from a very visual perspective, and then kind of build the mathematics around that piece. So here we go, everybody. It says on your paper, what is the standard form, sometimes called the rectangular form, of a complex number? And so if you remember from Algebra 2 or Pre-Calc 1, there is your a plus bi. So our nice complex number made up of the real part and the imaginary part. Okay, now we've done some operations with those. We're going to utilize those as well and actually build on those, extend beyond the operations that we've done in the past. So it says on your paper, it is often useful to picture a complex number. There it is. There's our a plus bi, everybody. Sometimes you see this, the z sort of representing that complex number as a plus bi in a complex plane. And what we're going to do is represent the horizontal axis of the plane being the real number line, the real axis. And that will, of course, come from the a value of the complex number. And then there's going to be a vertical axis intersecting it, and that will be what is called our imaginary axis, basically the imaginary number line. And that will come from the b value of the imaginary part. So what we'll go ahead and do is kind of draw and label a complex plane and plot some numbers on there, and really shouldn't be too bad. So everyone, if you would, give me what would be from like elementary school, just a nice horizontal real number line, that's all. And as a matter of fact, let's just kind of call this the real axis. And if you want, not that it's a big deal, why don't you go ahead and throw a tick mark in the middle there, and just a few tick marks on the side. However many you can fit in, doesn't have to be perfect. And if I asked you to plot any real number in existence, you would be able to find that on your real number line right here. Now, everybody, what we would like to do is create the imaginary axis intersecting that real axis right in the middle there. And so if you get an opportunity, for lack of a better description, this would be our pure imaginary number line. And again, just I'll label it as the imaginary axis. And so you can see that it is very, very similar to our good old-fashioned rectangular coordinate plane. It has sort of the horizontal piece, and it has the vertical piece. And that's exactly how we're going to treat finding these values, basically plotting these complex numbers on the complex plane. Any real number would show up on the real number line, the real axis. Any pure imaginary number would show up on the imaginary axis. Any complex number that has both parts with non-zero coefficients will end up somewhere in here. And so let's go ahead and find them. And again, the nice thing is, in terms of the location piece, really the real part would be the horizontal, the imaginary part would be the vertical, and then we can, of course, find any spot we need. So let's start this out, everybody. If you would, 3 plus 4i. So again, it's kind of a horizontal direction and a vertical direction. So I go 1, 2, 3 to the right, 1, 2, 3, 4 up, and that is where 3 plus 4i would be on the complex plane. That's it. I'll put a little a by it just to sort of denote exactly what we came with, what we got here. So 3 plus 4i is a. Alrighty, keep going here. How about this? Negative 1 minus 2i. So real part is negative 1, so that's the horizontal direction. The imaginary part deals with the negative 2i, so down 2. And everybody, not too difficult there. Throw in a letter b if you would. Now, as you can see, letter c, it's just a real number. And again, you've been plotting real numbers now for many, many years, and so just right on the real number line. There it is. There's letter c. So there's negative 3 right there. And again, I think I had implied this piece. Here's a pure imaginary number. And so an imaginary number will just end up on our imaginary axis. So everyone go down 1, 2, 3, 4. And there you have it. And so it is a way to plot something beyond just the real number system. What it requires is a secondary axis intersecting our good old-fashioned real number line. And once we have those two pieces together, we have a horizontal, we have a vertical, and then any complex number can now be placed within the plane. Okay, hope everyone's all right with that piece. I'm going to move to my next screen right here, and let's see what it says, and then go from there. So it says the absolute value of any number is defined as the distance from 0 on a number line. Everyone okay with that? When I ask you, and again, this is something you've seen for many years, absolute value very simply is how far it is away from 0 on the number line. In this case, it's the distance not just from 0, but from the intersection of the zeros, so 0, 0. So for the above complex numbers, draw a dotted line to represent each absolute value, and it says, is it possible to use the a and b values, so I'm just going to circle this piece, is it possible to use the a and b values of a complex number to find the absolute value of any complex number z equals a plus bi? All right, well, let me see if I can break this down for you, everyone. If you would, take a look at above, and if I want the absolute value of each of these 4 numbers, very simply, I just want to know exactly how far. Remember, I've used that phrase before, the direct distance. Keep that in mind if you would. The direct distance from here to the origin. So for letter B, that would be from here to here. How far is that right there? What is that distance? For letter C, everybody, try to get that in there. That's that distance. In fact, you could tell me the absolute value of -3. It's 3. 1, 2, 3 units away. This one's actually pretty easy. If I asked you what's the absolute value of -4i, you would go 1, 2, 3, 4. 4 units. So the absolute value of this one right here is 4. Well, the other ones are a little harder. So I'm curious, could you use the A, which was from here to here, and the B, which is from here to here, to get this piece? Now, don't do this on your paper. In fact, I probably shouldn't even be doing it up here, but does that help? Here's A, here's B, and here's the absolute value. So can you tell me a way to get that value right there? And does it sound like a little Pythagorean theorem would do well? This squared plus this squared equals that squared? And then I think we're in business. So we're going to use the horizontal squared, the vertical squared. That equals the direct distance squared. It just is slightly different than what we just saw. Do you remember talking about polar form of an ordered pair and a rectangular form of an ordered pair? Very, very similar, going from x and y to find r. And this is very much the same math. So first of all, let's put a yes right in there. Is it possible to use the a and the b? Absolutely. And we're just going to do a little Pythagorean theorem on that. And there it is. We have seen that calculation before. This is kind of the second time in this overall unit, and we will see it actually one more time even after this in a different topic of discussion. But there it is, guys, just a squared plus b squared, take the root, and there's our absolute value. Well, let's try a couple. So if I asked you for -2 plus 5i, and by the way, I'm going to go ahead and just sort of sketch this out very quickly, and if you're ahead of me on this, that's perfectly fine. But here's -2 plus 5i. And so what I'm looking for is the absolute value from here to here. And so all I have to do is take -2 squared plus 5 squared and square root it, and that should give me that. So in this case, everybody, I'm going to do a big square root. Just careful on this, -2 squared and 5 squared. It looks like I'm going to get 4 and 25, so I get root 29. And there it is. That's the absolute value for that particular number. That is exactly how far it is away from 0. This one, again, I think we've seen this before. Here would be 6i right up here. How far is that directly down to that origin? What is the absolute value? Well, we can count that out, but in this case, I would just do exactly what I came up with before. How about something like this? So a is 0, b is 6, 0 squared, and 6 squared, everyone. And looks like I just get square root of 36, which of course is 6. And you could see that here directly on the axis, 6 units down, perfect. So the absolute value is 6. The distance away from the origin is 6. How about one more here, just sort of ballparking this? Horizontal, vertical, everybody. So here's the 2 minus 3i. So there's the point, and there's the absolute value from there to there. And so as a result, let's go ahead and throw this in. Looks like I'll do, didn't need the parentheses around that one, but that's all right. So 2 squared and -3 squared. 4 and 9, everybody. should give us 13. Leave it just as is. Okay, so I told you that is a calculation that's going to come up for us quite a bit. So get used to that. Horizontal squared, vertical squared underneath the root. Okay, perfect. Let's keep going. So now it's going to be time in just a minute or two to start talking about the trigonometry connection with complex numbers. So here we go. It says in pre-calculus 1, we learned how to perform certain operations with complex numbers. So if you remember correctly, what we did, just nice and basic, very elementary, we added and we subtracted complex numbers. A little harder potentially, we also multiplied, and actually not significantly harder, but certainly the most difficult of the four, we also divided complex numbers. So your four basic operations dealing with complex numbers worked out great with a plus bi. Now it says to work effectively with powers and roots. So now two more operations on complex numbers. So powers and roots. It is useful to convert our a plus bi from what is called rectangular form. Everybody, rectangular form is going to be our a plus bi to something called polar. And it's called polar because the math is going to be identical to what we just did in our polar equations and polar coordinates. Or sometimes it's also called trigonometric form. So either way here, these two names are interchangeable. So let's see the connection. Represent a complex number in the first quadrant of the complex plane. Draw a reference triangle and label all relevant parts, and including the angle. So revisit the complex number in rectangular form. Is there a way to write the a value using r and theta? Is there a way to write the b value using r and theta? And that's what we'll do, guys. We're going to change our a plus bi to an entirely different representation. So you're going to see, obviously, anything we talk about dealing with complex numbers is very abstract and theoretical in nature, but there's some great math to behold here, so we'll take a look at it piecemeal. Okay, guys, here's what I'm thinking. If you would, can you give me just a complex plane on your paper? Real number line, imaginary number line. And let's go ahead and just find a complex number anywhere up in the first quadrant. It's just easier. And if you would, give me the absolute value going right to it. In fact, I'm going to just draw it solid, kind of like this. And by the way, shouldn't be a great shock that we're going to call that direct distance the radius. So there is your r value popping up again, and that should look very familiar to stuff we've been developing all semester long. Now, everyone, of course, here is my a plus bi. I'm going to bring that on down, everybody, and create my little reference triangle. And as I have said before, the horizontal piece would be a. That tells me how far to go over horizontally. The b value is a descriptor on how far up or down to go vertically. And so I have a, b, and r. So the absolute value will be our r. We already know the connection between those. But now that we've instilled this sort of terminal side going to our point, now there's the implication of an angle. And so everyone, throw a theta in place if you would. Okay. Now everyone, here's what I'm going to ask you to do. Give me an a plus bi, just sort of right here for now. And what we're going to basically do is change a using r and theta, and we're going to change b using r and theta. So this is rectangular form, or the standard form of a complex number. And guys, we're going to change a and b into r's and thetas. So let's see how it works. We know, of course, every angle has 6 ratios that go with it based on the 3 pieces: horizontal, vertical, and the direct distance. And so I'm going to use my primary 3 here. So the first one I'm going to do, everyone, is sine of theta. And that, of course, is going to be our vertical. Do you see our vertical here? Instead of the y, is just the b value. And over the direct, which is that right there. Is everyone okay with the fact that I'm going to want to take that r and bring it on up, just like I have done before? This is not new math, just a new topic for doing the same math. So there we go. There's b, everybody. R sine theta. So b is going to disappear in about 2 minutes. Let's do some more trig. Let's use another ratio on theta. And how about cosine, everybody? If I asked you for the cosine of this angle, you would tell me it's the horizontal over the direct. And so everybody, as a ratio, it is A over R. And you know the drill, of course. Everyone take that R and bring it on up. So that A value is R cosine theta. And as I mentioned, we're just getting off dealing with the polar coordinate system. And one of the things we came up with is the vertical, which we called y, was r sine theta. And the horizontal, which was x, was r cosine theta. Notice it's the same thing. It's just your horizontal and your vertical are just in a slightly different context. Instead of x and y, it's A and B. Well, guys, let's put that in place. So here's how it's going to play out, and I'll show you how this works. Typically, it's r cosine theta, and then r sine theta with the I there. Now we're going to write it in a slightly different way, but basically, as you can see, that is it. That's our A plus BI, now using R's and thetas. If you happen to notice here, everyone, there is an R in both terms, so typically you see the R factored out. So this is going to be a little new in its representation. So the R is factored out, and then I would get cosine of theta. Typically when you see this, everyone, the I comes out in front. Not that it matters, but the I typically comes out in front of the sine of theta. And everybody, big box around that piece. That is rectangular form. I'm just going to, as I'm thinking out loud here, I would encourage you to write a few things down. That's the rectangular form of a complex number. And guys, just using a little trigonometry here, what we came up with is what is called the polar, sometimes called the trigonometric form of the complex number. Let's see if we can get that in there, make it look a little nicer than I wrote it. So, the polar or trigonometric form of the complex number. All right, that's a lot to absorb there. Let's go ahead and fill this piece in, and then I just want to include one more ratio right in here. So breathe for a second, try to absorb that. Two different representations of a complex number that have a real part and an imaginary part. Okay, sometimes the complex number in polar or trig form is what's called r cis theta. So this is basically shorthand for this piece right here. I'll try to say the complete number as we go through our process, but every once in a while I might lapse into shorthand here. If I say r cis theta, that's this piece right here. And you can see it here is r cosine plus I sine theta. And that's just this. So if you hear this on occasion, it's really just this piece over here. Okay. Again, I wanted to include one more here as we'll see it on the back side. Don't forget the other one. Tangent of theta, of course, everybody, would be the vertical over the horizontal. So we're going to talk about going from A and B to theta, and that might be a big connection right there. Okay, a lot to absorb at this point, just setting up our complex numbers. So let's try it out. Here we go. On your paper, it should say the R value, so is sometimes called, well, it is called the modulus. And so I'll be using that word a little bit over the next couple days. And the angle, the theta, is called the argument. And typically, our theta will be in between 0 and 2 pi. Sort of there's our primary rotation. Again, we've been seeing that all semester long. We'll probably go back and forth. Everyone should be pretty comfortable now with both forms, either radians or degrees. So just keep that in mind, either from 0 to 2 pi or 0 to 360. And so what we're going to do is, just for today's lesson, for the most part, is just get comfortable converting from one to the other. So the easier way to do this is to go polar to rectangular first. Okay, and that's what we're going to do. That's example 2 in a nutshell. So it says, write the following numbers in rectangular form. And everybody, how about this just off to the side? What I mean by that, of course, is I want A plus BI. All right, so let's see if you know your unit circle. That would be great. These are good exact values from the unit circle. If they weren't, we would use a calculator and have to pull it off that way. So here's what I'm thinking. We know the cosine of 60 degrees. You know the cosine of 60 degrees as exactly 1/2. So that number right there is 1/2. And then plus, here's the I, and then you know this. This is a constant, of course. Sine of 60 degrees is √3/2. And so keep it nice and simple. Those values are given. The R value would theoretically distribute in, and I'm going to do exactly that. Sort of draw that arrow in. And everybody, 2 times 1/2 is just 1. 2 times √3/2. Well, the 2's would cancel. I'm hoping everybody sees that piece. And you would do this as 1 plus √3 times I, or 1 plus I√3. And that's it. So A plus BI. And there you have it, rectangular form. Okay, let's do letter B. So in this case, here's my R cosine theta plus I sine of theta. By the way, students ask this on occasion with this particular lesson. Will theta always be the same for a complex number? And so sorry for going back a screen here. But in this case, if I have a singular complex number, that terminal side has not changed, so theta is going to be the same for both parts. So long story short there, theta is always going to be identical for any particular complex number. Okay, so in this case, now let's go for it. Cosine of 135 degrees should be negative √2/2. I think you know that to be the case. And let's see, here's my plus, here's my I. Sine of 135 degrees, square root of 2/2, in this case positive. You know, if you grabbed your calculator and you sort of multiplied this out, that's fine. I'm going to leave it exact. So I see this as negative 5 √2/2, and then plus something along these lines right here. Again, so many different ways to write it, just as long as you keep the I as a factor by itself there. You know, it's really up to you. In fact, I'm kind of thinking I like it written in a slightly different way, but you can write it like that if you want. So 5 √2/2 times I don't know. Again, really doesn't matter. When all is said and done, as long as you have your A plus BI, you're good to go. Okay. How about this one for letter C? So same deal, everyone. I've got my 1.5 as my R value. Now I just have to remember my unit circle stuff. So cosine of pi/2, everyone, is 0. Absolutely. And then plus my I. And then sine of pi/2 is 1. And so I'm going to go ahead and do this. I have my 0 plus 1i inside. And of course, everybody, how about we distribute? I get my 0. And how about just 1.5i? So as you can see, this number up here in polar form is a way just to represent that pure imaginary number right there, 1.5i. They mean precisely the same thing. They are the identical numbers, just written differently, that's all. So as mentioned, going from polar to rectangular typically is not that big of a deal. Just really need to know your unit circle stuff. And if it's not something from the unit circle, you get it right off your calculator there. All right, on to the next. Now it gets a little harder. So I guess just a quick prerequisite description, and then we'll go ahead and try example 3. So now, in this case, we're going to go from rectangular to polar. And again, take a look at that math, everybody. Does it look familiar? Absolutely. So here we go, rectangular to polar. Horizontal squared and vertical squared underneath the root. That'll give us R, as it has before, and it now does again. And I said that tangent ratio is going to come up. If I have A and B, what's our connection to theta? Oh, it's definitely on the tangent ratio. And guys, do you remember, again, just the last couple days dealing with the polar coordinate system, sort of going from rectangular to polar there? When A was positive, we just had to do the inverse. When A was negative, remember we had to get in the right spot, and the limitations on the inverse made us sort of come up with a little rule of thumb. So don't forget to add your 180 degrees or pi radians when doing that. So we don't have to develop this because we already have. All of that bears out nicely. So let's just get some practice on it. You with me, of course, be great for you to work maybe a step ahead of me and then come back and see if you're on the right track. Hey, let's just see how we can do. I always go R first. I think it's just a little easier. That's just my opinion, by the way. So how about negative 2 squared? Negative 2 squared. Sounds good. And let's go 4 and 4 here, everybody, which would give me 8. So square root of 8. I would simplify the root if you can. I like a 2 root 2 there if you can pull that off. You know, we'll talk about when do you want to approximate, when do you want to simplify and keep it exact. I like that piece right here. So R is 2 root 2. Okay, now theta, everybody. Let's go ahead and get that theta. So we're going to do an inverse tangent. B over A, vertical over the horizontal. Here's the vertical, everybody. Here's the horizontal. And so I do that right there. Now, what is the one thing that I am forgetting, which I will now put in? When A is negative, we've seen this before, when the horizontal is negative, in order for us to get the proper angle measure, we would have to add 180 degrees. And because, just trying to be visual about this, if I asked you to plot negative 2 minus 2i on the complex plane, you would go 2 left, 2 down. There's quadrant 3, guys. This angle, unfortunately, will not be had on the calculator. So we need to go ahead and do this. All right, so I'm going to bring my calculator up, and let's go ahead and figure that out. So I'm going to go degree mode, by the way. If you want to go radians, you're more than welcome to, and if you can kind of see some of these values, that's great. So let's go inverse, tangent, negative 2 divided by negative 2. Close them off. How about we throw a 180 on the back end there? And there it is. There's your angle, 225. And take a look at the angle that I drew up here. Even as poorly as I drew that, and my goodness I did, you could see it's 225 degrees. Now just be careful. I've seen a lot of students over the years, they want to think about the polar coordinate system. And this is not the polar coordinate system. Even though the math is virtually identical, it's a complex number. So what we want to do is go back to our r cis theta. So long story short, guys, it's not an ordered pair. It's not this comma this. So we have to be careful on that, everyone. So our final answer would be 2 root 2 cosine 225 degrees plus I sine 225 degrees. That is the complex number negative 2 minus 2i in its polar form. So again, even though the math is virtually identical, the representation of your answers is different. It's not an ordered pair. Please don't write it as such. And so there you go. That's it. That is negative 2 minus 2i. Okay, good. Let's go ahead and do 2 more. So same scenario, everyone. I start out with r. Gives me a little confidence going in. I do this right here. And just be careful on this. I'm going to ask you to come up with that calculation right there. And you could just use your calculator if you want. 2 squared plus, and in parentheses, 2 root 3 squared, all under the root. I'm getting this. I'm looking at the math here, and I'm seeing 2 squared is 4. And then this is the tricky one, guys. 2 squared is 4. Root 3 squared is 3. So removing the parentheses, you get a product of 4 times 3 in there. That's what I'm seeing. And 4 times 3 is 12. So I get a 4 plus 12, long story short, which is 16. And so there's your R value. Nice. Okay. Again, 2 parts. Make sure you are able to come up with each. Let's go ahead and find theta. Vertical. Horizontal. Add 180, everybody? Nope, not here, not here. So that's positive, so just keep it. And you might know this. You know, the 2's cancel out there, and you would do an inverse tangent, really, of root 3. But I'll play it on the calculator. I don't mind. So 2 times square root of 3, and then divide by 2. Close them, and there's your 60. And we knew the inverse tangent of root 3 was 60 degrees. Okay, so now we want to write our r cis theta. So what that means, everybody, is r comes out, and it's cosine of 60 degrees and I sine of 60 degrees. Absolutely great. And it's always good to be visual with this. I'm just sort of looking at it. It doesn't have to be perfect, but 2 over, 2 root 3 up puts you right here. So R value is 4, and the angle is 60 degrees. Makes perfect sense. Be visual, especially as I'm looking at letter C. All right, one more here, everybody. So, and by the way, I'm going to take a look at this one initially. So negative 5i is down here. Keep that in the back of your mind if you would, because we're going to run into trouble in about 2 minutes here. Let's do r first, though, in the meantime. R is practically a gimme. A is 0. B is negative 5. And so I have those two pieces right here. Looks like 0 and 25. So square root of 25, I'm hoping you all see is 5. And I think we knew that to be the case. How far am I from the origin right here? I'm 5 units away, so r is 5. Now watch what happens here. Inverse tangent, vertical, horizontal, and let's go ahead and bring the calculator up. Maybe you're seeing it already, maybe not. Let's see, inverse tangent, negative 5, divide by 0. Uh-oh. And look what it says. I can't divide by 0. And so, guys, is this a proper tangent ratio? Is there an angle? Well, let me say it this way. This is an undefined ratio. And if you think about everything we've been going over, there are angles that have an undefined tangent ratio. So we have to sort of figure it out on our own here. Unfortunately, the calculator was not help. It doesn't mean that the angle doesn't exist. There's still an answer here. Because as a matter of fact, just sort of rotating around counterclockwise, that would be my angle. Unfortunately, as I said, the calculator wasn't able to give it to us because tangent happens to be undefined here. Hey guys, what is this angle? It looks like I'm rotating 90, 180, 270. And as you can see, here is an angle measure that unfortunately we weren't able to do an inverse tangent on, but we do know that tangent of 270 is undefined, so it still fits perfectly. By the way, if we were up here instead of down here, we would have gotten the same thing. It would have been a 90-degree angle, and we know tangent is undefined at 90. So you know it's either going to be up here or down here, either at 90 or 270. Well, anyway, here we go. So it's 5 cosine 270 and I sine 270. And there is the exact same number as negative 5i. Excellent. One more piece. And so just an interesting footnote, nothing more here. So it says Leonhard Euler, an 18th century mathematician, discovered a surprising connection between the number e and complex numbers in polar form. Euler's formula states that, and here's the situation that we'll look at momentarily, e raised to the I theta is equal to the cosine theta plus I sine theta. So a relationship between the number e and our complex number in polar form right here. Fascinating. Theta has to be in radians for this to work, so sort of as a real number. And watch what happens here. So everyone, if you would, what we're going to evaluate is this. Look at that, 3 great numbers all in play. So e raised to the I pi. Put that on your paper for me. And watch what this is. Watch what equation we get. And happens to be one of the more famous equations out there. Well, let's take a look. So e to the I pi, according to this, theta is pi, would be equal to the cosine of pi plus I sine of pi. All right, guys, think back to your unit circle, of course. What is the cosine of pi? So I'm looking at this equation right here, and the cosine of pi is -1. And plus, what is I times the sine of pi? Well, everyone, what is the sine of pi? 0. And so this is just 0, so it sort of goes away. And then notice what it says. This is our equation right here, but it says set your equation to 0. And what you have is a mathematical relationship amongst 5 of the most well-known numbers in all of mathematics. E, I, pi, 1, and 0, all related together beautifully. Excellent. Hey, I'm going to grab my calculator and check it out. But that is completely awesome. Let's see, I'm going to just change my mode here. I don't know if it's a necessity, but I'm going to go ahead over to complex number mode. You can just watch up here, and let's do this. E raised to the I pi, and then plus 1 should be, there it is, 0. Nice. So pretty fascinating mathematical relationship there. E, I, pi, 1, and 0. Okay, well, again, just an interesting footnote, no more there, but should be able to represent complex numbers now in 2 different forms: rectangular, a plus bi, and polar, r cis theta. Okay, guys, we're going to start some operations with these on the next couple notes worksheets. Be ready for some pretty heavy-duty math and some pretty good abstract theoretical stuff. All right, well, thanks for listening, and please let me know if you have any questions.